For this experiment, I investigated the effects of gravity and air resistance on projectile motion. This experiment touches on Newton's laws of motion, kinematics, and fluid dynamics. Their surroundings includes Earth gravitational fields and air resistance acting as a resistance force on a roll of tape. The primary goal of this lab is to analyze how air resistance affects the motion of a projectile and compare experimental data with computational models. By modeling both idealized projectile motion with gravity only and real-world motion, gravity plus drag. The fundamental principles of this lab is Newton's second law and all of its variations. Here are some noted equations. Here is the observed trajectory of the object. Using tracker software, I analyzed the trajectory of the roll of tape. I set the x-axis on the floor and placed the origin directly below the initial position of the thrown object. 2 meter sticks were used as calibration. Then, using GlowScript, I implemented a computational model incorporating only gravity and drag force. First, I set the initial conditions based on tracker data. Then, to calculate the net force, I use Newton's second law to calculate the force of gravity and the drag force. To calculate the drag force, I use the equation shown earlier, which involves B, the proportionality constant. When gravity is present, B equals 0. However, when taking into account air resistance, I estimated B to be about 0.03 based on my data. Lastly, in a while loop, I use variations of Newton's second law to update velocity and position at each time step. Here are the results from the model. The trajectory modeled with gravity only showed a perfect parabolic path consistent with kinematic equations in the absence of resistive forces. When adding drag force, the computational model better matched the observed data, showing a slightly reduced maximum height and slower descent due to the energy dissipation caused by air resistance. Using a spreadsheet, I plotted the following: the experimental trajectory from tracker analysis, computational model with gravity only, and computational model with gravity and drag. The model incorporating drag more closely followed the experimental data, demonstrating the importance of considering air resistance in projectile motion. However, it is important to note a possible source of error. Since the object was a roll of tape, the estimations for drag force are likely inaccurate, as it's likely rotating, which means the drag coefficient will constantly be changing. So what does this mean? Well, we know that terminal velocity occurs when the net force of a falling object is 0, meaning gravitational force is exactly balanced by the drag force. The velocity versus time graph for the gravity-only model shows continuous acceleration, meaning no terminal velocity was reached. The gravity plus drag model shows a reduction in acceleration over time, but the motion was way too short to reach terminal velocity. To observe terminal velocity, a similar experiment could be conducted by dropping the tape from a much greater height, such as a tall building, where the object could reach a steady state velocity. But what if the object were thrown straight up? Well, if the tape was thrown straight up with the same initial speed, the total time in the air would remain approximately the same in the idealized case without air resistance due to the symmetry of projectile motion. However, with air resistance, the ascent time would be shorter than the descent time, as drag reduces the upward velocity more quickly, leading to a faster deceleration on the way up and a more gradual acceleration on the way down. Thank you.